So the numbers seem to be building up nicely. Over 70 odd now, and it's less than 1 minute past the start time, which is really a good sign. This series of webinars were originally part of a week of activities organized by CICAG on open chemical sciences. We did 3 different intertwined programs, one on data, one on publishing, and one on these workshops. The workshops actually proved to be incredibly popular, and so we decided to spin them out, and they are now going to be a monthly event. So we have a whole range of workshops planned right up until the end of the year. We're now on the second of the workshops that we have planned for this session, and we have Greg Landrum talking today. This presentation is going to be on structure, validation, and standardization. It always strikes me as somewhat strange that when I see people doing model building and machine learning, that they spend huge amounts of time and effort getting the data ready in terms of the alphanumeric data, and then seem to just assume that all the structures are fine. I think Greg will probably persuade us that that's probably not the case, and that we have to spend as much time sorting out the structures as we do the rest of the data. Before I hand over to Greg, I just want a couple of housekeeping things. This is a 2-hour presentation, but we'll break after 1 hour to give everybody time to stretch their legs and things. If you have any questions, please put them into the Q&A box. We will then relay them to Greg and allow him to answer them. This series of meetings being sponsored by Liverpool Chirochem, and we have Tammy here, who can tell us a little bit about the company at the 1 hour break. So Greg, can I hand over to you and encourage you to start your presentation?
Thanks, Chris. So as Chris said, I am going to be talking about standardization, and I'm going to be talking about ways that you can be concerned about structures, or perhaps why you should be concerned about structures that you're using and how you can clean them up and check to see that they're okay. Depending upon the source where you get them from, this may be very, very important, or it could be less important, but it all depends on what you're doing, and I'll try and show you what's there. In the material that was sent around in advance, there was a link to a Colab notebook, so a Google Colab notebook. That's down at the bottom of this slide, and it'll be on the slide after next, in case you've forgotten that and you need to get there. So let's get started. I'll first tell you a little bit about who I am. If I can make my computer work. All right. So I'm the primary developer of the Rdkit. That's what I've been doing for quite a while. Professionally, I'm a senior scientist in the Rdkit group at the ETH in Zurich. I run a small consulting company, T5 Informatics, which provides Rdkit related support and services. And I have been working with the team at NIME, who provides an open source data analysis platform that many of you may know. I've been working with them for many years, and I continue to do that now. So I have a lot of different hats that I wear, but today I'm here wearing the Rdkit hat, and that's what I'll be talking about. So what we're going to do today, I'll give you a very quick overview of the Rdkit itself, and then some background on chemical standardization and validation, so why you should care, what the terms mean. I'll do an overview of an open source kind of shrink wrapped product, if you like, for doing structure validation and standardization, which is the Chemical Structure Pipeline. That addresses one very specific need, and you may find it useful. But then I will also do a hands-on overview of the capabilities that the Rdkit itself provides for doing molecular standardization and also validation. So kind of a hands-on tour of what the capabilities that are there. I'm doing all of this. You may have noticed this presentation is being done from Jupyter. I'll be doing everything from inside of Jupyter, and all of the notebooks will be in GitHub after this presentation. So I will send Chris a link, who can then send it to all the attendees to the repo at the end of the day. Good. So a quick intro to the Rdkit for those of you who don't know it. The most important two pieces of information are up at the top. So you install it in Python with conda install -c conda forge Rdkit, and then you get the most recent version. If you don't know how to use it, then the second link is also very important, which is a link to the documentation, specifically to the Getting Started guide, which will walk you through how to get started with using the Rdkit from inside of Python. We'll do a very small amount of that today, but I'm not going to get into the basics. I'll assume if you want to learn that, you can just go look in that documentation. So a little bit about the toolkit itself. It's open source, obviously. It's licensed with a business-friendly BSD license. By business-friendly, I mean that it is okay to build the Rdkit into commercial software. That's something that we encourage. We get a lot of great contributions back from the community, so from academics, also from pharma companies, but we also get a lot of major contributions coming in from chemical software companies. And part of that is because they can use the Rdkit in their commercial tools. The core data structures and algorithms are in C++, but most people don't care about that because they're not going to learn C++. And some of us know this, but most of you won't want to do that. So we have Python wrappers for normal people who want to use the Rdkit. We also have Java and C# wrappers. Recently, so in the last couple of releases, we've also started to provide a JavaScript wrapper. So you can use the Rdkit in web applications and have everything run in your web browser. This is not a full, doesn't provide all of the access to everything in the Rdkit, but a reasonable subset. At the moment, it actually doesn't have the standardization stuff in it. I realized that this week and started to fix that. So in the next release, you'll be able to do all of the stuff I show you today also in the JavaScript wrapper. It does all of the usual 2D and 3D things you'd expect. You can do fingerprints and descriptors for machine learning. You can use it inside PostgreSQL, which is a relational database. So you can do chemical capabilities in your relational database. And we also, one of the major ways that people use the Rdkit is using some nodes for KNIME. So this open source data analysis platform, there's a lot of Rdkit users who come in that way, but then also a lot who come in through Python. Rdkit.org is the main website. We support Mac, Windows, and Linux. A very important thing for me for the project is we do feature releases every 6 months. So around about March or April timeframe. So we just did a release at the very end of March. And then the next one will come in September or October. So that's every 6 months on a regular cycle. There's new features rolled out, and we do bug fixes and patches about once a month. The code is in GitHub. There's a link there for the organization. There are a couple of blogs that I do. This is for historic reasons. The Blogspot blog is the old one, and this other one is the new one. I haven't had time to do blog posts lately, but this new one is where those will land. And there's also a Twitter handle for people who care about such things. The documentation is here. I'm going to show you the documentation because I think it's super important. It's where you're going to get, so this is an open source tool. If you want support, the way you get it is from the documentation. That should be the first place you look. We have a couple of mailing lists. So Rdkit Discuss is also a good place to ask questions if you have them. We now have, as of a few months ago, we have this GitHub Discussions thing, which is kind of like Stack Overflow, kind of, inside of GitHub, connected just to the Rdkit. And then there's commercial support available for people who want that. If you, after this presentation, have questions about the Rdkit, the places to go for that would be Rdkit Discuss and to the discussions list, or the GitHub Discussions. This is the two primary resources for asking questions and for answering questions. Email sent to me asking questions, I'll just ask you to send to either of those two other places. And the reason I do that is because if I answer a question in a private email, I've just answered that question for one person. But if I answer a question on the mailing list or in GitHub Discussions, then it's available for everybody to find. So it really helps with the community to have questions be asked publicly, asked and answered publicly. Let's quickly look at the documentation because it is important. It is pretty good, I think, for an open source project. It could always be better. but I think we're doing okay. So this is what it looks like. This is updated with every release. There's an overview. There's some stuff about installation. There's the getting started guide, which is this thing I mentioned already, which kind of walks you through the basics of using the Rdkit. Explains how to read and write molecules, talks about calculating descriptors, modifying molecules, how to do molecular renderings, etc. So it's a good starting point for getting started with the Rdkit. A thing that I will point out, because I think it's quite important, a lot of the time in the documentation you see sample code. This is all in Python. A lot of the time you'll see code and an output. So for example, when you construct a molecule and call compute 2D coordinates, this function returns, in this case, 0. That means it works. When we build the Rdkit, we always make sure that when you run the documentation, it produces the same results. So actually, when you see the docs, you can be sure that they're correct because we actually test them. So we don't need to worry about our documentation getting out of date. There's also the Rdkit book, which for those of you who are old enough, this is roughly equivalent, or it's inspired by the idea of the daylight theory manual. This gets into some of the details of the guts behind what's going on for some of the code. So it talks about the aromaticity model. It talks about the extensions that we've added to smiles and smarts. It includes a reference for smarts. So if you can't remember what various queries mean, certainly in the Rdkit, this is the place to look because it includes basic smarts, but as well as the extensions that we've added to the language. This includes reference material as well for how we handle stereochemistry and how we think about that, how reactions work, and a bunch of information about the details of the program. So this is another good reference place to go for reference material. The last thing I'm going to call attention to is the cookbook. This was redone last year by Ven Scalfani, and he did a really nice job of getting this into a super usable form. This is also all tested, so we know that these individual recipes work. But what this is a set of recipes for doing particular tasks in the Rdkit in a very compact way. So for each recipe, you have what it's for. So this is including an atom index and a drawings in Jupyter. Here's some code that shows how to do it, along with some examples. Here's another one for including results from a calculation when you draw a molecule in Jupyter. Again, example code and what the output is. And there's just a bunch of different things. You can see there's a variety of different recipes in here. There are things for calculating descriptors, things for doing writing molecules out in different forms, some reaction tricks, and a bunch of other stuff. So this is another good place to go for reference material. Okay, good. Let me show you what the Rdkit looks like in Jupyter. For that, I'm just going to exit slide mode and we'll just go back and look at the notebook. So for people who haven't seen it, this is how I normally start a session with the Rdkit in Jupyter. So I import the chem module. That's where most of the chemistry code is. I import this IPython console thing because this brings in all of the Jupyter integration so that you do things like you can see molecules. I also bring in the drawing code. We'll see why in a moment. And then I always print out the version number of the Rdkit at the top of the notebook every time I use it. And that's so that when I go back later, if I have questions about the notebook, I can see what version I used. So the first thing is if I'm running in the notebook and I have a molecule as the result of a cell, so if the last line in the cell is just a molecule, the Rdkit notebook integration will show you a picture of the molecule. If you don't, without this integration turned on, you would just see some text saying that this is an Rdkit molecule at a particular address. I think the drawing is more useful. So we spend a lot of time on this integration. So there's my molecule. You have some control via this IPython console module. You have some control over the way the structures are drawn. So for example, if you, for whatever reason, don't want to see the structures cakalized, you can turn that off so it draws the structure with aromatic bonds. You can have it draw the atom indices in case you are working with atom indices in your code and you want to see what the atom indices on a molecule are, it's pretty easy to turn those on. All of the options that are available in this draw options object, which is really how you change things, they're all documented and there's a link in the notebook. Finally, as a display thing, if you have Py3DMol installed, this is another conda package. This builds a Jupyter integration for 3DMol.js, which is a 3D molecule viewer done by David Coase at the University of Pittsburgh. I mean, if you do that, then you can display 3D structures automatically. So here's an example where I construct a molecule from smiles. I add hydrogens to that because if I'm doing 3D structures, I need to have the hydrogens present. This embed molecule call is a way to generate a conformation for the molecule, so a 3D conformation. There is a random process involved in this, so I always seed that random process so I can know I can reproduce my conformations. And now, if I have the molecule as the last element of the cell, I get a 3D version of the molecule that I can interact with. So it becomes a really quick way to just take a look at 3D structures in the notebook. Obviously, this is all live, so I haven't been showing this. And because of the way it works, it's also quite fast, right? So it's easy for me to change the molecule and get a new 3D structure. Let me go back to benzoic acid though. Okay, sorry, this is not benzoic acid. I moved away. I had benzoic acid before, but it's not. It's just too boring. So, Chris, you probably know what the name of this is. I'm not good with naming.
I think it was phenylacetic acid.
Okay, thank you. I'm not enough of a chemist. If you don't want the 3D structures and if you don't have Py3D, if you don't have 3DMol.js installed, you can, this is what you'll see if you don't have it installed, but you can also just turn off the 3D. And when you do that, you see a 3D version or a 2D sketch of the 3D molecule. Basically what it does is it just sets all the Z coordinates to 0 and draws it. So sometimes this looks okay, but most of the time not. So that's why we did this 3D integration, right? You can also display multiple molecules. So here's an example where I'm just drawing two. So I have two molecules. I have benzoic acid and benzamidine. And I have those in a list. And there's this function draw moles to grid image, and that returns the drawing of the molecules on the grid. And we're going to be using this function a lot today to look at multiple molecules together. And as long as we're in Jupyter, changing the drawing options like we did before will also change the way moles to grid image works. So if I set that draw options atom indices true, then it'll draw benzoic acid and show the atom numbering. So as I'm showing you, using the code, using the Rdkit in the notebook actually changes what the code does. So if I call this moles to grid image function in a Python script, it behaves a little bit differently. And what those differences are documented here. So moles to grid image uses the Python console's draw options, and you can't pass one yourself. You have to modify those. The 4 functions: draw Rdkit bit, draw Rdkit bits, draw Morgan bit, and draw Morgan bits, return image objects instead of something else so that they display properly in the notebook. And then get substructure match and get substructure matches have been modified so that if you do a substructure match, it will show the matching substructure on the molecule. So let me show that. Let me get back to benzoic acid. And I'm going to just find the carboxylic acid on that. You can see when I do the substructure match, now if I display the molecule, it shows me the highlighting of where the substructure matched. And actually, I could have printed this out. So we could see that. You can see it's matching atoms 6, 7, and 8, and here it's highlighted atoms 6, 7, and 8. So this is just a nice bit of code that you get in the console. Okay, that's my very, very fast lightning overview to using the Rdkit in the notebook, as well as some of the things that are different. It's obviously not an overview of the Rdkit itself in any way. That's in the Getting Started guide. I'm now going to start talking about validation and standardization. Before I do that, I'll stop and see if there are any questions.
No, you're okay at the moment, Greg.
Good. Okay, so let's talk about standardization and validation. Oops. This is my problem with using this particular technology. I don't use it often enough and get the key bindings wrong. Okay, here we go. Okay, so what is molecular validation? When I'm using that term today, what I mean is molecular validation means ensuring that a molecule is reasonable or legal for the purpose at hand. By legal, I mean just chemically sensible for whatever it is that you want to do. This can be very context dependent. So for example, if you're just doing normal chemistry stuff, you probably just want molecules that are chemically valid. If you're dealing with compounds that are produced in flames, or you're doing combustion chemistry, you probably have a very different idea of what's valid than an organic chemist doing medicinal chemistry. And so you'd probably want to use different validation rules. Similarly, if you want to do virtual screening and suggest compounds that might actually be tested in an assay, you may also want to have a different definition of valid, because you may want to filter out molecules that have very reactive groups. Right? You may want to define for your purpose anything that has a metal atom, or something very reactive is no longer valid. So this concept of validation is fairly flexible and context dependent. Some examples of things that one might do for validity, I mentioned some of this already, is valence rules are obeyed. So for example, a 3-coordinate neutral oxygen is not allowed, right? That's not chemically reasonable most of the time. Compounds that have bad elements or elements I don't want to see are removed. So a lot of the time, if I'm doing something like a virtual screen, or if I'm building a machine learning model, I'm going to filter out the things that have transition metals in them, because probably I don't have a good representation of the structure for those anyway. And the descriptors that I'm using aren't going to model those well, so I'll just get rid of them. I mentioned already, sometimes you might want to remove things that have bad substructures, so things that have reactive groups, etc. There's a number of different things you can imagine fitting in this category of validation, so it needs to be flexible. Standardization is different. Standardization is actually modifying the molecule. So here I give you a molecule, and you're going to apply a set of standard operations to that molecule to get it ready for whatever it is you're planning on doing with it. There's no one-size-fits-all solution for this either, because obviously this is very context dependent, right? If I'm going to do virtual screening, it's different from if I want to register this in my corporate database. And if I'm going to go into a 3D model, I'm probably going to prepare the molecules differently than if I'm going into a 2D model. Some example operations that one might do here are functional group normalizations. So for example, taking hypervalent nitro, the 5 coordinates of single bond to the nitrogen and then 2 double bonds to the 2 oxygens, and turning that into the charge separated form. This is something the Rdkit does. You might want to remove redundant chirality specifications, right? So if there's a chirality specification on an atom that isn't actually chiral, it makes sense to remove that, because you don't want to carry around information that doesn't make sense. Often you would want to neutralize molecules. You may want to actually charge molecules, right? You may want to have a standardization step that charges molecules to represent what they would look like at physiological pH. This is something that very often done before you send things in for a docking run, for example. I don't want to get any expectations set up. The Rdkit does not have anything for doing that last bit. So charging to physiological pH is not something we know how to do. I can neutralize molecules, but I can't do that physiological pH. We don't have a pKa calculator, that's why. Removing salts and fragments is another common task, and this is a mistake that people make all the time when working, even with very, very highly curated data like the data from Chembl. People will pull data out from Chembl and they will build models based upon that, and they will forget to remove the salts. Sometimes it's okay to do that, but most of the time it's not. Most of the time you're getting results that don't, the descriptors that you're doing, if you're doing chemical fingerprints, the descriptors really don't make much sense. And another thing that people often like to do is Tautomer canonicalization, and I'll say some words about that later. Okay, so let's look at some real world examples for why we might care about that. And for that, we're going to look at some compounds from PubChem Substance. For people who don't know, PubChem has an enormous amount of data in it, and the data is kind of divided into two sets of compounds. There's PubChem Substance and there's PubChem Compound. PubChem Compound is the pre-processed version or the standardized version of the things from PubChem Substance. So when people submit data to PubChem, that lands in Substance. When they pre-process it and look to see if they've seen it before and clean it up for their database, then it's in Compound. So the number of things in Compound is substantially smaller than the number of things in Substance. You can have duplicates in Substance because multiple vendors or multiple people submit the same compound drawn in different ways. Those all show up in Substance. So what we're going to do is look at Substance. I downloaded this first set of 500,000. I don't think this is actually full. There's not a full 500,000 in there, but I downloaded a big block of compounds from Substance. For people who are using the colab, the wget command for downloading that is here. So this is where that file that I worked with is. And if you run the colab and actually execute this, it'll download it so you have a local copy. Oh, I forgot to mention the colab. I forgot to show it. I said I was going to show it. Okay, so let me just quickly walk through what this is. For people who don't know, colab is a Google hosted thing that allows you to execute Python Jupyter notebooks on their computing resources. Execute and share on their computing resources. So it's a really nice way to share notebooks with people and have them be able to run them. You have Jupyter. This is not exactly Jupyter, but it's a lot like Jupyter that you can work with. You can see I can execute shell commands. In this case, you can see the version of Python that it runs is 3.7. Colab does not support conda directly, unfortunately. So in order to install the Rdkit, we have to do a trick. This used to be incredibly painful, but now it's gotten quite easy because Jaime at the Charité in Berlin has put together a really nice conda package for this. So if you pip install this and then import it and do conda colab.install, it does everything required to allow you to do conda installs into your colab notebook. So this next step is installing the Rdkit as well as the Kemble structure pipeline into the colab notebook, and then you can just see I'm just showing that it works here. So you have the link to this notebook and can try it out if you like. A thing to be aware of, executing these first few lines takes a while. So you should expect it to spend a few minutes going through these first few steps. It's definitely easier to run things locally if you can. Okay, sorry, back to PubChem Substance. So what I'm going to do is...
Greg, there's a question that might be a good time to answer, actually.
Okay.
Is there a difference using this approach instead of, for example, paddle descriptor or standardizer from Chemaxon or any other cheminformatics package, I guess, really, in terms of... Yeah.
Every standardizer is different, so there's not a one-size-fits-all solution. They all do things slightly differently. They all tend to do more or less the same set of things, but differently. They all tend to be configurable, so you can pick which things you want to use, and I'll demonstrate all of this and show it as we're going through. So I'll talk about a couple of different standardizers. I'll mention a couple of other ones, but we're going to focus on the Rdkit one just because there are numerous options out there. I'm going to use here the one that I know best.
That's great.
Okay, so what I'm going to do is read a set of molecules in from this SD file. For people who don't know it, this is showing how to read from a gzip SD file with the Rdkit. And what I'm going to do is read in the molecules, and I'm going to collect the molecules that fail the Rdkit standard validation. So the Rdkit standard validation is executed by this function called sanitize mol, and we'll say considerably more about this in a moment later when I'm actually walking through the pieces, but this runs through all of the Rdkit standard validation operations as well as some basic standardization work. And if this fails, I append the molecule to this failed list. So what I'm doing basically is I'm reading molecules out of this SD file until I find 100 that have a validation problem so that the Rdkit won't read. That's what this loop is doing. I do a little bit of pre-processing on this. I make a copy of them, and then I do a little bit of pre-processing so that we can display them properly. And then this bit of code, I'll walk through it. What I'm going to do is I have this interactive widget that allows me to browse through those failing molecules. So let me show you how I did that. So if you have Jupyter installed, if you have Jupyter Notebook installed, you have IPy widgets. And IPy widgets provides this interact function. You can use the function as a decorator. So if I have a function called show moles that takes an argument and a list of molecules, let me explain the molecule and then I'll explain the function and then I'll explain what interact does. Inside the function, I'm going to construct a molecule drawer. So this is the specific way that you draw, this is the way that you draw a specific molecule in the Rdkit to an SVG. I then draw the molecule, I set some options, I draw the molecule. So I want to draw from this list, M's, I want to draw the IDX molecule. So that's M's of IDX. I draw it, I finish the drawing, and then I have this return an SVG object. This SVG object is something that Jupyter knows how to display. So let me just show you what happens if I call this by itself. So if I show the third molecule from my list, it returns something that Jupyter knows how to display. And so calling that function gives me something that shows the molecule. And then by putting this @interact decorator on it, what I do is I tell Jupyter that it should look at the arguments that are up here. I'm telling it that this IDX argument is drawn from the list of numbers that go from 0 to the length of the list of molecules, and that this M's argument is a fixed number, it shouldn't change, and it's always going to be equal to that CMS. CMS is this list of molecules that I just built up here. So when I execute this, we already saw it, when I execute this, what I get is a dropdown, and the dropdown is set by this IDX argument. So it's 0 to len of CMS. So there should be 100 molecules in here. There aren't. Interesting. I wonder why I don't have the demo effect biting me. Ah, okay. I'm not quite sure what happened. Anyway, I have my set of molecules. I'm sorry, I'm somewhat disturbed by this. I'm going to go execute this again so we can make sure that this is working as it should. Okay, that's better. That's much better. This for people who haven't used Jupyter a lot, what just happened to me is a thing that happens all of the time in Jupyter. And I had this variable CMS. It's not a very good variable name, and I use it multiple times in the notebook. So further down, I had redefined CMS, and I was now looking at the new version in the old code. So you have to be very careful about this in Jupyter if you aren't used to it. Okay, so anyway, these are the molecules. We can now browse through the molecules that had problems. And one of the things you will notice as I'm going through these is that many of these molecules contain a metal atom. And it's pretty typical if you have molecules coming from standard file formats that the Rdkit is not going to like them if they are organometallic species because the bonding that's drawn in our files is typically not really right. for these. So the way these bonds are drawn, specifically the bonds from this nitrogen to that technetium, this is not actually a single bond, it's a dative bond, but that's not what's in the file format. And so the Rdkit complains because it sees a 4-coordinate neutral nitrogen, and it says this does not make any sense, right? Nitrogen cannot be 4-coordinate and neutral. It needs to be, it cannot be 4-valent and neutral. It would need to be positively charged to have this valent state. But if I look through the molecules, you can see most of them have metals. So that suggests to me the first thing I want to do when looking through this PubChem set, the first very crude validation thing I want to do is I want to get rid of all the molecules that contain transition metals, because I'm obviously not dealing with those properly. So what I did for that, just for the purposes of this notebook, is I create a very simple definition of the atoms, a smarts definition that includes the atoms that I am willing to accept. So this is, so it's hydrogen. I have the alkali metals and the alkali earths. I have carbon and nitrogen and silicon and phosphorus and sulfur, and then I have the halogens. And I'm not willing to accept anything else, just for this simple example. So let's run through that now. This is going to take a little bit longer to execute because now it's not even looking at the molecules. I'm not including the molecules that include metal atoms when I'm trying to find failures. So I'm not having nearly as many failures. I have to look through way more molecules. So this is going to take a little bit longer to execute. And then we'll look at those molecules one at a time to see what other kinds of weird things are in PubChem Substance. Again, the point I'm doing this is I just want to demonstrate what real-world data sets look like, what the molecules in real-world data sets can look like, and why validation and pre-processing is important. So let me do that bit of work there. Now let's see what we have left. Okay, so let's browse through here and see what we've got. So these molecules have an unhappy nitrogen atom. Again, this is a 4-coordinate. It's a 4-valent neutral nitrogen, which is never going to be a happy thing in the Rdkit. So if we wanted to actually read these molecules in, we'd have to figure out what the author of this file really meant by that and try and figure out how to fix it. Because this is certainly not what they meant. This is not chemically reasonable. Here's another one of those 4-coordinate neutral nitrogens. We have to figure that out. Here is a hypervalent chlorine. N- with 3 bonds to it is also not a thing, right? So this is the kind of stuff that the Rdkit is normally rejecting. Here's another lovely thing. So basically what I want to show by going through this is just the kind of stuff that one finds. Now this is a different case. So there's actually nothing wrong with this molecule. This is a hydroborane, but this includes a kind of bonding that the Rdkit doesn't know, and it's not represented properly in the input file. So these 2-coordinate hydrogens, these are 3-center 2-electron bonds, but they're represented in the mole file as 2 single bonds, which is wrong. And so the Rdkit doesn't accept those. Anyway, we can browse through and get a sense for what's the kind of weird stuff that's in PubChem Substance. Now, when they do pre-processing on their side, when they do their standardization steps, some of this stuff they clean up, and some of these just fall by the wayside and don't ever end up in PubChem compound. So that's why you want to do this pre-processing. If you do learning on a thing like this, if you put this into a model or you put this into your corporate database, you're going to have problems every time you encounter it. So that's my motivation by looking at some very much real-world data and kind of the ugly side of things. Before I move on, are there questions about that and why we really care about validation and standardization?
There is one question. What is the role of bad atoms variable?
The bad atoms variable. Oh, okay. So I didn't walk through what this code actually does. So here I define a query molecule. So I construct a molecule from smarts. And then I loop. Again, I open up this the gzip file and I create a supplier from it. So this is the way you read molecules from an SD file in the Rdkit. And I'm going to loop over each of the molecules in the supplier. And if the molecule has a substructure match to that bad atoms query, then I continue the loop, which means don't do any more work, just go on to the next molecule. So I'm using this bad atoms query to identify problematic atoms in the molecule. So molecules that have problematic atoms. Does that answer the question?
I think so, yes.
Okay.
Said yes, thanks.
Cool. Okay. Actually, I can, by opening in the second monitor, I can see the Q&A.
Okay.
Is there an easy way to silence the Rdkit error warning if needed? Yes, you can do that. You can, let me see the best place for me to do that. Let me show you an error, I want to demonstrate this actually works. So if this is trying to create a 3-coordinate neutral oxygen, which generates an error. There is this Rdkit logger where I can disable the logs. And the way I turn them all off is like that. So turn off all the logs, and now I don't see the log messages anymore. I can turn them back on again with enable log. There's another question if there's any way to reconstruct invalid molecule smiles, the closest valid version. There is probably not, but depends upon what is invalid and what isn't. And we'll, by doing some of these.
What you mean by closest?
Yeah. So I'll mention some of this later when we actually look at the standardization, but standardization does some of this. So for example, let me see. It's pretty obvious here what this substructure is supposed to be, right? This is an azide. So it's pretty clear what that's supposed to be. We just have to fix it. And so sorry, it's not an azide. What is that? Chris, help.
It is an azide.
Isn't azide N3?
Oh, sorry. I'm not. Oh, I guess that's supposed to be imine.
Okay. In cases where it's clear, where there's common mistakes, the Rdkit has code that fixes it, and we'll talk about some of that. Oh, okay. So there's a question about if there's a grammar error in the smile. So if it includes an unclosed parentheses, no, there is not. There's no grammar correction. So if the smiles is syntactically wrong, it can't fix it. And then Asmarna asked if there's any way to correct the valence and include in the list to continue for further calculation. So when we talk about standardization, I'll show some of the valence correction stuff that happens and the way that works. Okay, there's a question about fingerprints. We'll come to that. Please park that question towards the end, and if we have time, I'm happy to talk about that. That doesn't really fit into the rest of this particular presentation, but I'd be happy to come back to that at the end if we have time. Okay, so we've gone through some examples to motivate why one might want to do standardization, and saw some validation steps as well too. Like we're filtering, I'm showing you what the Rdkit default validation does of filtering out these molecules that it doesn't like. But let's see if there's ways that we can make this more flexible. Okay, so by default, what the Rdkit does, and we were just seeing this, but let me describe it. So by default, when you read a molecule in, it performs a set of validation and standardization steps every time. And the Rdkit calls this standardization, so cleaning up standardization. You can disable this or run it independently, but by default, it does it. So you actually have to take an active step in order to deal with molecules that have chemistry problems. It is important to know that the standardization step, in addition to this cleanup and validation, it also does some chemistry perception. So for example, perceiving aromaticity, rings, implicit valence, and hybridization, and that's used in the rest of the code. So if you need information about rings and you don't sanitize the molecule, you will need to tell the Rdkit to generate the information about rings. And we saw that actually in a notebook that I was using where I've read these molecules and failed mols in without doing sanitization. So they don't have any information about valence, which is what this update property cache does. And they don't have any information about rings, and it needs information about rings to draw the molecules properly. So this get sem SSSR is the way to get ring information. So I'm doing these two chemistry perception steps to get the information that we need to draw the molecules properly. And it's important not to forget those steps if you don't sanitize molecules. In general, you should always sanitize molecules, right? So let me go off on a rant before I show you how to fix these problems. The reason the Rdkit is so strict about chemistry is because if it was not strict about chemistry, every person who used it would ignore all of the warnings that it produces and put garbage compounds into their data sets or into their database. Right. So there's a reason that if you go through old databases or collections of compounds, you see 3-coordinate neutral oxygen or 4-coordinate neutral nitrogen, right? You see things that don't make any chemical sense. And the reason they're in those data sets is because the chemistry toolkit that people were using didn't allow them to go in there, right? It might have produced a warning and said, oh, there's a bad compound, but people ignore warnings. So I believe it's much better to have the chemistry correct and reasonable. And then that's the default state. And if you want something where you have strange chemistry, like for example, you're doing flame, combustion chemistry, or you are working with organometallics and you want to you have your own way of thinking about this bonding and you want the Rdkit to work with the molecule, you can do that. You just turn the sanitization off. Okay, so let me show you, let's go back to the notebook and let's look at some of that validation in the Rdkit itself. So here I'm going to construct 3-coordinate neutral oxygen, and we just saw that in the previous notebook, and you see that you get a complaint from the Rdkit that the explicit valence on atom 1, which is the explicit valence is 3, is greater than permitted. If I show you the molecule without sanitizing it, this is the molecule, right? So that is not chemically reasonable. The Rdkit rejects it by default, the validation. Bad aromatic systems, this is a very common example. This happens in SMILES because there are certain chemistry toolkits, particularly older versions of certain chemistry toolkits that produce SMILES, which was incorrect. This SMILES is incorrect. So the Rdkit, if you try and read this, it says it can't caicalize the molecule and it tells you which atoms it can't caicalize. Caicalizing is taking an aromatic ring and assigning single and double bonds around the ring. So it's telling you which ring it can't do. If we look at the molecule and turn that sanitization step off, this is the molecule. This molecule needs a hydrogen on one of those 2 nitrogens. Right? Otherwise, it's not correct. It's just not reasonable unless there's a hydrogen on one of those 2 nitrogens. If I say that it's aromatic, you can't figure out where that hydrogen is because it could be on either one. The Rdkit does not guess. So it doesn't guess and say, oh, it's on this one or it's on that one. It just says, okay, you didn't tell me enough information to clean this molecule up, so I'm going to reject it by default. If we give it a SMILES where we've told it where the nitrogen is, the molecule parses fine, and you can see it caicalizes it, and I get the proper structure. So this is just another one of those validation steps. And this is one that happens all the time. So if you're using the Rdkit and you see this error, cannot caicalize molecule, it is almost always because there's a nitrogen in there that doesn't, in an aromatic bond that, sorry, there's a aromatic heterocycle that has a heteroatom in it that should have a hydrogen on it, and that hydrogen is not indicated in the smiles. So this is the example of that. There's also some standardization that happens by default when you read molecules in. So there's some standard functional groups that are cleaned up. So for example, in these examples, the left-hand molecule is the molecule that I provided in the smiles, and the right-hand molecule is what the Rdkit does to it when I read it in. So if I read in a neutral, if I read in this 5-coordinate hypervalent form of nitro, the Rdkit by default standardizes it to the charge separated form. Similarly for N oxides, pyridine and oxides, it takes it to the charge separated form. Again, here, that's a 4-coordinate nitrogen. It has a positive charge. Everything's happy. Here's an azide. This is a common way of misdrawing an azide. Here we have a 5-coordinate neutral nitrogen. This you don't see so much anymore. This used to show up all the time because of an older version of another chemistry toolkit would represent azides this way. This is what that's supposed to be. I apologize. This is not the best drawing. This should be N minus. The minus is there and hard to see. And this should be N plus, and the plus is there and hard to see. Example of phosphorus chemistry that is cleaned up by default. Here's some hypervalent halogens. This happens with all of the halogens. Well, sorry, not fluorine. This happens with chlorine, bromine, and iodine. If you give them in these hypervalent forms, they're all split into the charge separated form. And the other thing that happens when you read molecules in by default is that invalid stereochemistry specifications are removed. So for example, if I provide a molecule where I draw this, so this is not a chiral molecule. If I draw this and put a wedged bond on it, the default behavior of the Rdkit is to take that wedge bond right back off again and give you the molecule that has the correct indication that it is not, in fact, this is not a stereocenter. The same thing happens with double bonds. Unfortunately, the way we draw double bonds, you can't see that the double bond stereo isn't there because by drawing a double bond, it automatically has stereo, right? It's automatically either cis or trans whenever you draw it. So there's no way to see that in a rendering unless you make the middle bond crossed, which the Rdkit does not do by default. But in this case, I'm specifying the stereochemistry of a double bond. And you can see if I don't sanitize that the single bonds still have bond directionality associated with them, which means there's still some information about stereochemistry there. If I do the normal sanitization, that directionality information is not there. I apologize, this one is a little bit in the weeds. This is a little bit detailed because there's not, as I said, there's not an easy way to show this. Okay, so I see a question came up, what percentage of bad smiles are in PubChem? It depends upon how you define bad and which set you're talking about. If you're talking about substance or compound. Compound has, most of them will pass through the Rdkit. Smiles is not the native format of PubChem, right? The native format of PubChem is the mole file. So the smiles has been generated from the mole file. It's not the best way to figure out whether or not the structure is valid. If the question is what percentage of smiles in PubChem are syntactically invalid, so which ones have parentheses that are not closed, it should be 0 because those are generated by a good chemistry toolkit. They should all be perfectly legal smiles. Okay, Brian Cole asks if it's reasonable to use the standardization built into Inchy. It depends, and I'll say something about that a bit later when I talk about Tautomers. And okay, there's a question about how the validation and standardization differ if working in KNIME using the Rdkit nodes. The Rdkit KNIME nodes work if you're just using the working with molecules as normal with those nodes and don't change any configuration, all of the validation and standardization that I just showed happens. You can turn that off though in the nodes. You can tell it to do partial sanitization in the mole to Rdkit node. Okay. I am going to now do an overview of a shrink-wrapped. Actually, before I move on to something new, why don't we do the break now?
I was just about to say the same thing. I think that's a very good idea. So we'll do a 5-minute break and let people stretch their legs. Tammy, do you want to just say a few words?
Hi, thanks. Yeah, I just want to start by saying thanks to Greg and the many others who have contributed to Rdkit over the last few years. We at LCC are sponsoring these 4 workshops as we understand the importance of computational chemistry in the world of research, which is what we are ultimately here to support. For those of you who don't know, Liverpool Chirochem, we are a chemical technology innovator, and we are ultimately on a mission to accelerate small molecule drug discovery through exploring 3D chemical space. At the minute, we currently have thousands of novel 3D-rich multifunctional fragments and scaffolds, which we have recently used to develop a very exciting 3D virtual library of over 1 million compounds. So that's just a brief introduction to LCC, but if you would like to know any more, or if you would like to reach out, please contact us on our LinkedIn page or via the chat function on our website. Thank you.
Yeah, thanks very much, Tammy.
Thank you.
We'll reconvene in 5 minutes then.
Chris, when do you want to start again?
Yeah, I think we should start now, actually. I just wanted to make one comment about the smiles in PubChem. There are 2 versions of smiles in PubChem. There is the canonical smiles and the isomeric smiles. And if you want to include stereochemistry, I think you have to use the isomeric one.
Yeah, that goes back, the reason for the difference in the nomenclature there goes back to the daylight days, actually, where smiles was generated. You would get canonical smiles without isomeric smiles. The isomeric smiles in PubChem is also canonical. It's just not as a different name. That's a pretty old nomenclature.
Okay, I think looking, we're still up to 100 people or so so should go on.
Cool. Okay. So I'll do a quick overview now and then demo for you the Kemble structure pipeline, which is an open source tool for doing the validation and standardization rules that are used when compounds are loaded into Kemble. I guess probably most of you are familiar with Kemble. This was published last year, and the Kemble team started using it in Kemble itself last year as well. So the open access link to the open access paper is here. The code is, of course, also all open source and is in GitHub, link there, and it's all based on the Rdkit. So the components of this, there are 3 components. The first one is the validation step, and that is called the checker. So that takes a mol block or an Rdkit molecule, and it tests the validity of that. It does the validation check and flags errors. And these are errors. It's different from what the Rdkit normal validation does. This is from what the Kemble team thinks are errors, and it also assigns scores to those, and we'll see that in a minute. Then there's a standardizer, and the standardizer is applied to molecules that pass the checker. And again, I'll mention that, or I'll show the details in the notebook itself. And this applies a set of standardization rules that the Kemble team has put together, the Kemble curation team has put together over the course of quite a while, since basically Kemble's been in operation. And this is the steps that are applied to molecules to get them ready to be loaded in, get them ready to be sent to the INCHI code where the INCHI identifier is generated, which is what's used to deduplicate molecules in Kemble. And then there's the last piece is get parent. And get parent, you give it a molecule and it removes salts and solvents and gives you back just the parent molecule. And so this is a standardization step. This is often known as salt stripping or solvent stripping. This is, I mentioned already, this is a very important thing to do, and working with almost all the time is an important thing to do before actually really working with molecules that come from data sets. There's extensive detail about those components themselves and what they do in the wiki, as well as in the publication. So the open access publication was linked on a previous page, but you can also just look in the wiki. And now let's go and actually look at what this looks like when we apply it to PubChem Substance. So this is another Jupyter notebook. I read in the import the Rdkit the way I always do, and this time I'm also importing the Kimball structure pipeline. Now I'm printing out two versions at the top, so I'll print out the Rdkit version and the Kimball pipeline structure pipeline version. I'm going to go through that PubChem Substance file that we were working with before, and I'm just going to read the first 1,000 records. And in this case, I'm not processing the molecules. I'm not reading them into the Rdkit. I'm just getting the mole blocks, getting the actual SD records out of that file, and then making a list of all of the SD records so that corresponds to the molecules in the file. So let's go ahead and just quickly look at what these look like. So I can take a look at the first one. So this is a SD block. If you were to look at that SD file, this is the first molecule record in that file. And the way you can do that, this is brain dead text processing. I'm just looping over all the lines in the file. I'm finding this is the record separator in an SD file, and I'm just appending all of the things into these individual records. Once I have one of these records, so this is a mole block followed by some data. Once I have that, I can then pass that to the Kimball structure pipeline. And this check mole block function, which takes one of those mole blocks or SD records and gives you back whether or not problems are found. And in this case, it returns an empty tuple, which means no alerts, everything is fine with that molecule. So here, what I'm going to do, I pulled the first 1,000 records from this. I'm going to loop over those, the first 1,000, call check mole block on each of them. And if that returns something that's not this empty tuple, I'm going to print out the index number and what the result returned by the check mole block is. So that's what's here. And you can see, so for the first, so molecule 1, which is actually the second molecule, molecule 1, there are 3 alerts registered. So the first is that the INCHI code had to accept an unusual valence. The second is also from an INCHI code, and that's that protons had to be added and removed. Third is also from INCHI, that had this SD block had a metal that needed to be disconnected. Each of these warnings or flags that comes back is assigned a score, and that's what this number is. So that's a score of 6. Each of these is a score of 2. The score for a molecule is the highest score of all of the individual alerts that it gets. And if anything exceeds 6, then the molecule is not considered validated and it's rejected. It's not loadable into Kimball. So they don't pre-process it. It's handled differently in the Kimball pipeline. So here's an example. Molecule 4 has unknown elements, and that's an INCHI code of 7. That molecule will not be loaded. So let's look at those. Here, I'm not going to go through the individual code or all of the code in the Schomel function, but this is another one of those interact functions. I'm looping over all of the records. And for each of them, I'm printing out what you get from the check mole block function, and then I'm showing the molecule. So let's go look at number 1. Okay, you can see INCHI accepted unusual valences and protons were added and removed. And if you look, this is another one of these technetium compounds. So the unusual valences were likely around the technetium. The one that I want to highlight is this number 7, where the INCHI said there's unknown elements. So let's take a look at that. And you can see here, there are a bunch of dummy atoms in this. And INCHI, this is, at least in the older versions of INCHI, it didn't know anything about dummy atoms. And it's still, this is not actually an element, so this molecule would not be loaded as is in Dikembe. I mean, we can do this, and we can look at the rest of these and see. So again, here's another example of a molecule that has unknown elements. I'm guessing if we look, we will find there's a dummy atom over here at the edge, as well as here. These are probably polymers that are just in the mol blocks as in the SD file as mol blocks. Okay, so that's the checker. So what the way the chemical structure pipeline works is the molecule, the mol block is sent through the checker, and if the score is below 7, then it's sent to the standardizer, which does a bunch of cleanup operations. And then the third step that I mentioned, the third step is this get parents, which removes salts and solvents from the molecule. So I'm not going to show each of those in incredible detail. Instead, what I'm going to do is just loop through the first 1,000 molecules. And for the ones that worked, we will see the pre-processed molecule, so the molecule that has been standardized, and then the parent. So this is the one where the salts have been stripped, and there's another thing, and I left it on this molecule not accidentally. The other thing that's different is the isotopes are all set to their defaults in the parent compound. So isotopic information is removed for the parent. Both of these molecules would be loaded into Dikembe. So the one on the right without the isotopic information is considered the parent of the other one. So let's go look at a few more of these so we can see the difference between the non-standardized and the standardized. The non-standardized and the parent, the standardized and the parent. Left-hand molecule is a standardized structure. This structure is neutral. Each of the anions, each of the hydroxy groups or the carboxylic acid has a corresponding counterion. So this is neutral. And now when I get the parent for this, it removes the salts and neutralizes the molecule again. And this is what I end up with. So this is the parent of that. And we can just browse through this and see some of the other ones. Sometimes this get parent step, you can see here, there's nothing changes for get parent because there's no additional fragments in this, right? It's just the molecule itself. Here's an example where the isotope was removed, right? So we go from isotopically labeled ammonia to just normal ammonia. I'm not going to go through all of these. There's 1,000 of them, but you have the notebook. You can go through and look yourself. I just want to give the idea of what's happening in this process of this. Here we have the standardized molecule, and then there's the get parent. What I haven't drawn in this, because they're occasionally pretty ugly, I haven't drawn the molecule before standardization. That was just ended up being too ugly to draw. Okay, before I move off this, so this was a very quick overview of what the chemical structure pipeline does. I'm going to show you now, I'm going to talk about the pieces that are in the Rdkit, so the Rdkit's mol standardize functionality, which was used to build a lot of this. So I'll show you if you wanted to re-implement something that does something like the chemical structure pipeline, but not exactly the same, how you would do that, what the pieces are, or if just in your own workflow, you have particular standardization steps that you want to do. I'm going to show you how to do that. And that's what I'm going to spend the rest of the time on. But before I move off this, are there questions about the chemical structure pipeline that people haven't asked yet?
Perhaps one question I sometimes get is, how do you decide which is about the roles of the components of a salt? How do you decide what is a salt and the counterion, as it were, particularly if you get organic bases or something like this?
Yeah, that can get very tricky. And to be honest, I don't exactly remember what the chemical, there's a list of solvents. I know that. It's probably easiest for us just to go look at the code. Okay. Solvents and salts are defined in a list.
Okay.
And then that's really, it's kind of the only safe way to do it is to have a list. The problem, you will miss things when you do that, right? But it's a safe way to do it. And there's a bunch of rules, right? This is the wiki, and it's showing some of the details of what goes into this. So if the get parent steps of removing the solvents or removing the salts, if that removes everything, then it's not done. Right? So if you remove everything, that's the same as removing nothing. So it just doesn't do it. So it doesn't reduce the molecule to nothing. And the other one is the duplicate fragments. So duplication, which means after you neutralize and remove H's from the fragments, if you end up with duplicate fragments, it will remove the duplicates. Okay, so there's some questions about the speed of this. In the way, it doesn't really matter. It doesn't take a horribly long time. So you only do this once, right? You process molecules once and then you're done with it. So in order to process, if you run millions and it takes an hour, then that's fine because you only process the millions once for an hour. So I don't know exactly, I don't remember, we did do benchmarking of this. I don't remember what the results are, but it's not, I think doing 1 million compounds in less than an hour is completely reasonable. I would be surprised if it took longer than that. But again, standardization, you only have to do it once. You can do it in parallel. You're not doing this process over and over again. Okay, let me go back to the slides. Okay, some other, okay. So there's another question, I forgot to show this. Can the standardizer process anything other than SD blocks? Can one pass a molecule object? And the answer to that is yes. In general, it's safer to use the mole block if you have it, because then the Rdkit hasn't messed with it, right? The Rdkit hasn't done any of its standardization on it. So that's just taking the raw input and giving it to the Chembl structure pipeline. And that's the way the Chembl team uses it. However, all of these functions have, so you see I have this standardized mole block, and I have get parent mole block. All of these have a mole equivalent. So there's standardized mole that takes an Rdkit molecule and returns an Rdkit molecule. And there's get parent mole, which takes an Rdkit molecule and returns an Rdkit molecule. Same with the checker, there's a mole version of that. There's a question of how accurate it is. That's a question that doesn't really have an answer because there's no way to define what accurate means in this case. It's accurate enough for the Chembl team, it's what they use. So if you want to add some refinement to that question, some further detail as to what you're looking for, I'd be happy to answer it later. Here's some other Rdkit related possibilities for doing standardization. There are many options out there, also non-Rdkit related, but I'm advertising for the Rdkit today, so I'm not going to talk about those. But the Rdkit related possibilities, there's the Standardizer, which Francis Atkinson wrote as part of an IMI, as part of the eTalks project. That doesn't seem actively maintained, but it's here if you want to try that. This is an older tool developed at Novartis, the Avalon Toolkit StruCheck functionality. This is a very powerful and flexible piece of software, but it is not trivial to use and it's not particularly well documented. But that's available within the Rdkit. This also doesn't seem extremely actively maintained. There is an Rdkit reimplementation of that we did when I was, when I was still at Novartis. Oh crap, now I'm lost. Oh, okay, I see what happened. Chris, remember how I mentioned you can edit slides while viewing them? That's what I just did.
Most impressive.
Yeah, that's terrible. I don't recommend anybody use this. So it's in the Rdkit. It's not built by default. You actually have to go through some work to do it if you want to, and I would recommend you not do that. And then there's MolVS. MolVS was written by Matt Swain, who's on this call. And that was the inspiration for the Rdkit's mole standardize, which is what I'm going to talk about next. So let's look at that. So mole standardize in the Rdkit. This started as a port of Matt's MolVS code. And the idea of what we wanted to do was take MolVS, re-implement it in C++ so that it's perhaps a bit faster, but also so that we can use it from everywhere that the Rdkit is used. And we also wanted to bring it over into the Rdkit core. And this was done by Susan Leung as in her 2018 Google Summer of Code project. Since then, we've been working on completing it, and it's been extended and expanded since the original project. This is part of the Rdkit core. It's when you download the Rdkit, you will get mol standardize. So what does it do? The options that are available at the moment, so this is as of the current version. You can normalize, which is applying standard transformations. That's doing things like cleaning up functional groups. You can neutralize molecules, so you make the overall molecule neutral when possible. You can do reionization, which rearranges charges to something that's hopefully more stable, at least as stable, as accurate as we can be with the rules that we provide there. They're fairly conservative. You can do some work with tautomers, so you can enumerate all the tautomers of a molecule. You can score those tautomers and you can pick a canonical tautomer. You can do metal atom disconnections. Remember, I mentioned there's often the problems with bonds to metals in the file formats that we use. There's one standard kind of pre-processing step is just to break all of the bonds to the metal and have it treat it like a salt. This obviously is not correct, but it's what you get if you just read all single bonds out of a mol file is also not correct. So you kind of have to choose which way you want to be wrong. Disconnecting is not always the right thing to do, but it's fairly common. This is what Inchi does when you read molecules that have metals in, and it solves some of the problems with those. You can also have it strip fragments, so that's removing salts, metals, and solvents. We saw that already. And then there's some validation code in there. So the validation here, there's a number of different validation rules that you can use, but the one that's new relative to what we've seen to this point is you can also add lists of allowed and disallowed atoms. So you can say, okay, here's a list of atom types defined either by atomic number or by smarts query or whatever. You say, there's my list of atom types. If the molecule contains anything that's not from this list of atom types, reject it. So it allows you to do some very, very conservative validation. You can also flip that on its head and say, if it contains anything from this list, disallow it. And that's the usual one of, don't give me things that have metals, or don't give me things that have reactive groups, reactive atoms. So those are the options that are available, operations, and I'm going to show you what that looks like in a notebook. So back in Jupyter, still the Rdkit, still the most recent version. Now what I did here is, rather than going one at a time, I created a bunch of molecules, and I'm going to read them in. For each of them, I'm going to call the mol standardized normalize function, which is this cleaning up functional groups. And then I'm going to do a plot. So I show the moles to grid image where I have pairs of molecules. So this is before, this is the input molecule, that's after, that's the normalized molecule, before, after, et cetera. And I'm going to talk through these in a minute, or I'll talk through these as we go. And yeah, what I've picked is examples which demonstrate this default cleanup steps. So here is, and I apologize, I'm going to get my nomenclature wrong on this. Chris, please correct me when I do get it wrong. So this is, it takes the charge separated form of sulfones and gives you the more normal sulfone. Did I get that one right?
That's right, yeah.
Okay, the next one I don't remember.
Sulfoxide.
Sulfoxide, thank you. It does the opposite for sulfoxides. So it takes the double bonded for the keto form of the sulfoxide and turns it into the Zwitter ion. The reason this happens in my mind, and there's other reasons to do this, but the one I think is most important is these groups are frequently chiral, and it really bothers me to see a double bond to an atom that's chiral. So I think it's much cleaner to look at it this way, to have single bonds. These phosphorus groups, I'm not going to try to name it, nor put Chris on the spot to name this particular one, but this is an example of a fairly commonly occurring phosphorus motif that gets tidied up as follows. Here's a bad azide that gets drawn that way. The Rdkit does this one by default. Further weird nitrogen cases, nitrogen always shows up in these things. There's all kinds of weird nitrogen cases. Here's a strange cyano drawing that happens sometimes, and it gets cleaned up to that. These are some 1,3 and 1,5 shifts. So this particular bit of ugliness is changed to that, and this particular bit of ugliness is changed to that. So these are the standard rules that are there. I want to make a comment because I realized I had done this to entertain myself as I was putting the notebook together, and I forgot to turn it off. You may notice that all of these things are drawn with kind of wavy lines, and the font is kind of weird. That's one of the things we added to the Rdkit in the last release is comic mode. So when you do comic mode, it tries to make molecules look like what they would look like in XKCD. And I left that on. So we're seeing them in comic mode. I actually kind of like it. I think it looks nice, but it's why the lines aren't all straight.
There's a couple of questions that might be worth answering.
Let's see. So is there a way to switch off the Rdkit standardization when reading in a mol or SD file? Yes, that's turning standardization off. So there's a sanitize flag for all of the molecule parsers. You set sanitize equals off. And then, as I mentioned before, you probably may need to pre-compute or recompute some of the calculated properties. Brian asks, is the Standardizer Tautomer enumerator rule-based or more algorithmic? It's rule-based, and I'll show what it looks like. And there's a standard paper that has rules for doing Tautomer enumeration, and it uses those rules. Okay, next step in that you can do with mol standardize is neutralizing molecules. This is taking a molecule and, when possible, reducing the total charge of the molecule to 0. And so again, I'm doing before and after. The way you do that using mol standardize itself is you create a uncharger object and you call uncharger.uncharge. I'm going to apologize in advance. The API that you have to use to work with this code is incredibly inconsistent. So in this case, I have a convenience function called normalize, where I give it a molecule and it gives me the normalized molecule. For the uncharger, I have to construct an uncharger object and then call that on the molecule, and you get that back. This is dumb. This is my fault. So it's me, bad API designer. I need to go back and fix this and add convenience functions for the uncharger. So the next version of the Rdkit, this is going to be easier to do. I apologize to you now that you have to do this work. The uncharger, just again, it tries to neutralize the molecule. So here's a before and after. So benzoic acid or benzoate is neutralized to benzoic acid. If I have the sodium there, this overall molecule is neutral. So doing the neutralizer doesn't do anything to it. Here I have a nitrogen with a 4-coordinate nitrogen with a hydrogen on it. I can neutralize that to the 3-coordinate nitrogen. Quaternary amines. This has quaternary amines. This has no hydrogens to remove, so there is no way that I can neutralize this molecule. So this N+ stays N+ after neutralization. As an example, this molecule has a net charge. So if one of these two O- had a hydrogen on it, then the molecule would be neutral and nothing would happen. But because the molecule has a net charge, it goes in and it just starts removing things. And so I end up with a neutral molecule at the end. Right, so if it starts off neutral, it stays neutral. But because it has a charge, it removes all the charges and I end up with a neutral molecule. Here's an example where I have, again, a quaternary amine. So here I have a positive charge. There's 2 negative charges, so I can remove one of the negative charges. And then I'm neutral again. And in this case, it is the OH that's removed. By default, the atom that is, when there's a choice to be made, by default, the atom that is neutralized is chosen canonically. So regardless of how you provide the input ordering to this, you will always get the same output. It does not attempt to do this particular thing using any chemistry rules. That's what the reionizer is for later. It really just tries to pick a canonical choice. So in this case, it will always be the OH, the oxygen that gets hydrogen attached. Quick question. So Marcus asked if you can change molecules. And yes, there's a way to take an Rdkit molecule and turn it into a editable molecule and add and remove atoms.
I think that says charge molecules.
Oh, charge. I'm sorry, charge. You can reionize, which is the next step. It is charge. I need better glasses. You can reionize. There is nothing that will automatically add a charge to molecules. So you can't, for example, do protonation to physiological pH. We don't have a pKa model for that. If you want to write your own rules, normalization rules, you can write normalization rules that recognize groups that you think should be protonated, and you can protonate them yourself, but there's nothing built in. Okay, reionization moves charge around. So for example, in this case, the carboxylic acid, there's nothing, the benzoate, there's nothing to move. Here, when I have a benzoic acid where I also have an O-, there are two possible places this negative charge can live. It can be either be on this oxygen or on that oxygen, and the reionizer will move it to put it onto the more acidic, it'll put the charge onto, remove the hydrogen from the more acidic center, put the charge on the more basic center. There's a set of rules for figuring out what should happen in this case. And this is just a simple example of that. So that's reionization. Again, takes what comes out of the neutralizer where you have a charge left over and just moves it around to put it in hopefully a more stable point. Okay, Brian asks if there's a neutralizer that drives each individual atom to neutral instead of the overall molecule. No, it focuses on the overall molecule. So if the molecule is neutral, it does not attempt to do anything to it. One could write that, but it's not there. So we talked about parents. There's a number of different ways of finding parents. In what's in the Rdkit, we have, or in the mole standardize, at the moment, the only thing that's implemented is parent fragment. There are some other options that will be added for the next release that are not yet there. This is one of the things we didn't get to finish during Susan's summer project, and it still hasn't been finished, but I'm going to get this done for the next release. So here's a couple of examples of that. So the find parent fragment, in this case, we have the sodium benzoate, and the parent for that is just the benzoate by itself, so it removes the salt. Here's an example where I have a solvate. So there's a benzene floating around in here with my drug molecule, and then when I call the fragment parent, it removes that. There are a number of different rules that you can provide for how it identifies which fragment gets removed. In this particular case, I don't remember what the default is, so I'm not going to finish that sentence. But there's a number of different rules. You can have it prefer organic fragments. You can have it choose the largest fragment. Matt, maybe you remember, does MolVS have an option to provide a list of salts? Do you remember? If you're talking, you're muted. Okay, we can't hear Matt. I'll look into that and try and figure that out. Okay, the other thing which is useful often is to combine neutralization with the parent fragment. And we saw this from the output of the Kemble structure pipeline. So it finds the parent fragment and then neutralizes it. And so to do that, I just make this fragment parent call, and then I uncharge that. It's really simple, right? So sodium benzoate gets the parent of that is the benzoate, and then I neutralize that and I end up with benzoic acid. And the my drug-like molecule down at the bottom, or this actually is a marketed drug. It's not drug-like, or it's extremely drug-like. It's a drug. When I remove the phenyl here, it doesn't do anything because it's a neutral molecule. I mentioned the metal disconnector already. This is quite simple. So I start with a molecule that has, the way you use this is you construct a metal disconnector object, and then you call the disconnect method on your molecule. It gives you back a new molecule. And so here, this is what I start with. So I have an FeO bond. When I disconnect it, I no longer have the FeO bond, and you notice that it's done the charge separation. So the atom that's left ends up with a negative charge, and the metal atom ends up with a positive. Something similar with aluminum. There are some metals that by default are not removed. So for example, if you do mercuric dimethyl mercury, so methyl mercury methyl, and you disconnect that, this does not get disconnected. So the organic mercury is not disconnected by default. Similarly, here's a Grignard reagent. So I have a magnesium bond and also a sodium bond. The sodium oxygen bond is broken, but the magnesium metal bond is not, or organic bond is not broken. And there's some rules that you can change, modify to change this behavior if you want to get some fine-grained control over which metals are disconnected. Now I want to walk through, I showed you all of the individual examples. I want to walk through and apply it to a real molecule. I'm going to use esomeprazole as my example. This is probably my favorite molecule for things like this because this molecule is awesome. It has just about everything that you would ever want to use for chem informatics teaching in it. It also happens to be one of the largest selling drugs. So for people who don't know it, this is esomeprazole is Nexium. I think it's either Nexium or Prilosec. It is a proton pump inhibitor. It's an anti-ulcer medication. It's very, very broadly sold, and it's over the counter in many countries. It's been around for a long time. This is how it's marketed. So it's a magnesium salt. You have in the marketed formulation, you have you have a magnesium and then 2 instances of the esomeprazole, the API itself. So let's go through and apply the individual steps of mole standardized to this. So I'll start by calling cleanup. And cleanup, we saw this already. It takes the sulfoxide and converts that into a single bond. So now I have, for each of my fragments, I have the S plus with a single bond to the O minus, but otherwise nothing changes in this molecule. When I remove fragments with fragment parent, it strips out the magnesium 2+ and then just leaves me with one of the esomeprazole pieces. So this is the core bit. So if I was going to do machine learning on esomeprazole, this is probably what I should provide. You will notice, however, it does still have a charge. So we probably may want to neutralize that before doing any further work. So I neutralize it. We saw this again already. So I take the uncharger, I do that on esomeprazole, get the fragment parent, and this is what I have left. So at this point, I now have a molecule that I could theoretically generate fingerprints for or generate a 3D structure for and do some work with. It's always worth checking what the tautomer situation is. So this particular molecule there, if you spend a second looking at it, you realize that these 2 nitrogens, probably either one of the hydrogen could be on either one of them. And there may be some other tautomerically active centers in here. So it's worth asking mole standardized to go ahead and enumerate the tautomers just so we can look at them. Okay, well, let me start with those. So what I do here is I have a tautomer enumerator object that's generated here. I enumerate the tautomers of the parent, and then I score each of those with the tautomer enumerator object. And now I'm going to display each of the tautomers along with their score. So You can see there are some odd tautomers in this, some things that you, perhaps the first few, you may not actually like to see if you look at it with a chemist size. The last two, so this last one is what we actually started with, and this one is the one where I've just flipped the hydrogen to the other side of the ring. These are the two highest scoring based on the rules that are there. So if I were to ask for the canonical tautomer, it's going to pick one of these two. And the way it chooses which one to pick is which one has the, it's using the canonical smiles. So once it's gotten things down to so that the scores are the same, it uses canonical smiles and it takes the canonical smiles that's less than the other one. So, or maybe greater than, I don't remember. It doesn't matter. It takes one of them and that gives you a canonical tautomer. A very important thing to remember about this whole process is this is just a canonical tautomer. The idea is not that this is the tautomer that's going to be present in any particular solvent at any particular temperature. It's not the most stable tautomer. It's not the, I don't know, I can think of a number of other things that it's not, but what it is it's canonical. So you will, regardless of how you draw the input molecule, you will always get this as the output tautomer. And I hope if a chemist looks at any of these, the chemist won't look at them and go, oh my God, that's a horrible tautomer. This is the difference to the ANCHI algorithm. So the ANCHI algorithm also generates canonical tautomer, but there a lot of the time, if you look at it as a chemist, the tautomers are pretty horrible. So we try to make it so that the tautomers don't look really bad. But again, we're not trying to generate the most stable tautomer in any particular solvent or temperature combination or in gas phase. It's just something that's reasonable and is canonical. So this, in the end, if we were doing Tautomer normalization, this is probably what we would start with if we were doing Tautomer canonicalization while doing our registration. However, I think that one should think very carefully before doing that. So it is likely, if I put these two tautomers in solution, that they will interact, that they will interconvert with each other. It's pretty likely that those are going to interconvert. In fact, it's known that they probably do interconvert, except for under particular circumstances. However, it is possible to isolate both of those tautomers. And in fact, omeprazole, which is the enantiomeric version of S-omeprazole, omeprazole exhibits tautomeric polymorphism. So this tautomer crystallizes in a different tautomer, a different polymorph than this tautomer. So it's a real world situation. I didn't just make this up, right? This is not some obscure molecule. It's a real world situation where you get different crystal structures for those two different tautomers. If you go through the PDB, or CSD, there are many, many, many instances where you can find compounds that are tautomers of each other, where you can isolate one tautomer or the other. If you want to build a database, or if you want to do computation on one tautomer or the other, you need to not be doing the tautomer canonicalization, right? Because if I want to do a computation on this tautomer and my pre-processing pipeline always converts it to that one, I've lost. So you need to think carefully before you do that tautomer canonicalization step going into any chemical operation or anything you're going to do working with molecules. So it's not just 3D things where this make a difference. These have different fingerprints from each other, right? So depending upon which fingerprint you do, these are not the same molecule. They'll get different fingerprints, you'll get different machine learning results, etc. So you should be careful with this. It's worth realizing that tautomers, yes, they do interconvert, but it is often possible to isolate one or the other. And if you're building a system, you probably want to be sure that your system will support allowing you to lock in the tautomer. Because if you know you have one, you want to be sure that you stick with that. That was my tautomer rant.
Just a quick note. I see Matt has put a comment in the chat about your question about solvents, etc.
Okay, let me pull that up. Okay, so Matt's this as a fragment. Okay, so it does take a list of salts and solvents for a default list, but it can also pick the largest fragment. The Rdkit mole standardize implements what's in MolVS. So unless that was added in the last year or two, which I don't think it was, then this is what the Rdkit does as well. Thank you, Matt. Okay, a quick one just before I move off the Tautomer point, before I finish my rant on that. If you do want to determine whether or not two molecules are tautomers of each other, there's a very easy way to do that in the Rdkit without going through this expensive Tautomer normalization thing, or without converting them to inches, which is, by the way, converting them to inches is another way to figure out if two molecules are tautomers of each other. But there's a simpler way to do it, which is using this RD-mol hash functionality. The RD-mol hash functionality has a hash that it can calculate for molecules that normalizes tautomers as part of the hash. And so these two tautomers, these are the hashes for them. And you can see that those are identical to each other. So if you have two molecules which are tautomers of each other, this RD-mol hash called with the het atom tautomer flag will generate hashes indicating that those molecules are the same. So that's an easy way to check if molecules are identical except for tautomerism. Give credit where credit is due. This is something that Roger Sale came up with, and the guys at NextMove Software contributed this code to the Rdkit. So that was Noel of Boyle did a lot of that work as well as Roger. This is really useful. It's a really nice way to identify whether or not two molecules are tautomerically equivalent. Okay, let me go back to my, unless there's any other questions about mole standardize or my tautomer rant. And give it a second for those questions to show up, and then I'll start to switch back to my slides. Okay, so that's it. That's what I wanted to go through. I'm happy to do more examples. There's a couple questions that I'm going to come back to and answer now. If you have other questions, please put them in the chat. And otherwise, once I've answered those two questions, I think we're basically done. Again, if there's questions, if you have questions for me about the Rdkit or about mole standardize, the two best places, or the best place to do that is with this Github Discussions, the Github Discussions tab in the Rdkit GitHub repo. And there's also commercial support. So of course, if you have a commercial support contract, I'm perfectly happy to answer questions. Okay, let me come back to the questions that were asked in the Q&A. So I'll do Brian's first. Is it reasonable to use the standardization built into Inchy? And is there a way to do that without a round trip through the Inchy string? Inchy does have a standardization process. If you're happy with what it does to the molecule, that's a perfectly fine one to use. It does do Tautomer normalization though, and it does do metal disconnecting. So if you're happy with both of those, then it's a okay way to do things. I am not aware of any way to do that without going through the Inchy string. So you really have to convert the molecule into an Inchy string and then the Inchy string back to a molecule to get the final form. Is there a solution for standardizing reactions? If you mean a reaction, which is molecule 1 plus molecule 2 goes to molecule 3, you can do that by standardizing the individual molecules. If you mean a transformation, which is like a query plus query goes to query, then standardization is not going to work with that. So there's no automated way to do it. If you're working with reactions where the molecules are, where you actually have real molecules going in, then you can standardize the individual molecules. A giant caveat to that is that by doing that, in rearranging the bonds, the reaction may not look like it makes sense anymore. I don't have an example to show, but it's if you rearrange the bonds, like if you remove a double bond that was being broken in your standardization process, the reaction is going to look kind of silly. The Jupyter notebooks that I showed today are going to be in GitHub. I will send Chris a link to that so that he can send it around to everybody. So all the notebooks will be in GitHub. I'm not going to put the data in GitHub because you can just get that from PubChem, but all the notebooks will be there. Can the mole standardization Rdkit do the canonicalization automatically? Can you canonicalize the Tautomer automatically? Yeah, there's a way to get the canonical Tautomer. That's simple. Okay, so there was another question was if there's a fingerprint to represent the stereochemical difference between compounds once they've been standardized. Most of the Rdkit fingerprints do not use stereochemistry. So most of the fingerprints available in the Rdkit do not use stereochemistry. So you have to look a little bit. So the Rdkit's Morgan fingerprint, if you turn on the use stereochemistry option, it will use stereo and when it's doing the calculation. And so then molecules which are stereoisomers of each other will generate different fingerprints. So that is the way to do that if you want to do that. It is, in general, it's not the best fingerprint for doing chirality. We don't really have a good answer for that. And I believe it's only atomic chirality. I believe it doesn't do double bonds, double bond stereochemistry. But I can always check that.
Okay,
Other questions? Okay.
I think that's about it. That's a fantastic presentation, Greg, and many thanks for that. I think, as I said at the start, this is a key component of anybody who's dealing with molecules, and so it's really invaluable having these this detailed explanation and all the pitfalls you can fall into as well. I thought it was really good.
Thanks for suggesting it. For people don't know, this was Chris's idea. He kind of said, "Oh, do you want to do something about the standardization?" Like, sure, that sounds fun.
Yeah, and you did a great presentation, so thanks for that. As I said, I'll make sure all of the notebooks and things like this are available, and the video will be available once I've edited it in due course on the CICAG YouTube channel. So, and again, we'll send the links to everybody who registered probably end of the week or something like that. Okay.
Looks like there may be one other question. So someone was trying to raise their hand, but it's better. I just typed this in the chat box. It's better to type the question in the Q&A. We're not doing the other form of questions. Or just use the GitHub Discussions is another way to do this. Okay, yeah, I don't see anything.
No. Perhaps you've already answered it. Yeah.
Can always hope.
Yeah. Well, again, thank you very much, Greg. Great presentation. Just to remind everybody that this is a monthly event, and so there'll be another one in a month's time from David Coves. Oh, here you go. You've got your question now. But in the chat. Are there any particular libraries that need to be installed?
Yeah, so you need to have the Rdkit installed. I covered that at the beginning. So when I share the slides, take a look at the slides. It'll tell you what you need to do. You must have missed the beginning. Yeah. Go ahead, Chris.
Okay, that's great. Well, thank you again, once again. And as I say, we'll make sure everybody gets all contacted for all the resources from this. And I look forward to many more people using the Rdkit.
Thanks, Chris, and thanks to all of you for your attention and for the questions.
Okay, bye-bye then, everybody.
Thank you. Bye.
Thanks, Tammy.
Bye.